Yes, good morning, friends. And today, one of my students, Kadam Sharma, he had commented. Actually, I have got actually 88 comments. Okay, in past 24 hours. Okay, in past 24 hours, I have got 88 comments. And out of those 88 comments, I was not able to see the majority of comments. Okay, I am really sorry for it. But one comment I saw, which was by Kadam Sharma. Okay, so the comment which Kadam Sharma made was that please complete the syllabus on time and please increase the duration of the class. Sure, your demand will be fulfilled. Okay, but in order to increase the duration of the class, I need the laptop, and my laptop is at repairing shop. Okay, laptop is at repairing shop. I am making the video right now with the help of my tablet. Okay, with the help of my tab I am making the video, so don't worry, you will get everything. Okay, but have a little patience. Okay, because I have my college also. Okay, so it is really difficult to do everything. Okay, so let's start from here. That there is a up to here we had learned. Okay, that corresponding to px, the x component of momentum. Up to here we had learnt in the previous classes. So now we will start from here, that there is a linear quantum mechanical operator corresponding to every observable. Now what does this mean? Okay, there is an operator corresponding to every observable, and in elementary quantum mechanics this operator which corresponds to every observable is linear in nature. What does it mean by linear? By linear, it simply means that it will satisfy this rule. Okay, d by dx u plus v. Suppose, for example, differentiation is a linear operator. Why is it a linear operator? Because when I take the d by dx of u plus v, I simply get du by dx plus dv by dx, right? I simply get this, right? So linear operator simply means that it follows the law of distributivity. Okay, it follows the law of distributivity. It is simply it implies that only. So there is a linear quantum mechanical operator corresponding to every observable. This is what is fundamental of quantum mechanics, elementary quantum mechanics. Now what are the various types of operators we will see now. And I had already told you one thing, that our operator is of the form, suppose this is operator which is applied on psi, then it will yield you some observable multiplied by psi, right? I had told you this. Okay, so in a similar fashion we have various kinds of operators. So in classical mechanics we have position, in classical mechanics we have momentum. So all those will correspond to an operator in quantum. So the position operator in quantum, it becomes something like this, that when I say that it is position operator, if it is along the x direction, suppose if I measure the position along x direction in classical mechanics, then the corresponding quantum mechanical term will be the x hat operator, x cap or x hat. Okay, this can be read in two ways. It can be either read as x hat, or it can be read as x cap also. Okay, but I will say hat only over here. So x hat or x, it is basically your multiplication by x. Y hat or y, it is basically your multiplication by y. And z hat or z, it is basically your multiplication by z, right? So this is what is position operator. Now it is not necessary that always an operator will mean it is multiplication. No, it is not like that. This position operator is such an operator that when it is applied on some observable, when it is not observable, when it is applied to a wave function. For example, if I say x hat, okay, if I say x hat psi, okay, so it will simply imply that it is equal to x psi. Okay, that is what it means x hat, your operator x hat is simply equal to your algebraic multiplication. Okay, But momentum operator is not like this. For example, momentum operator, as we have found out in the previous classes, what have we found out? We have found out that momentum operator looks something like this. We have found out this, right? That momentum operators look something like this. So momentum operator is different. It is not equivalent to algebraic multiplication. But your position operator is equal to, so over here, if this would have been suppose position, then x cap would have come over here, or capital X might have come over here, and that would have been equal to operator, and your this thing would have been simply x, because it is equivalent to algebraic multiplication, right? So such thing would have been there in case of position operator. Okay, so now over here, if the position operator is simply, if it is in the x direction, that it simply means that multiplication by x. If it is in the y direction, simply it means that it will be multiplication by y. If it is in z direction, simply it will mean that it is multiplication by z. Okay, now similarly, if a fixed direction is not there, suppose instead of x cap, y cap, z cap, I have suppose r hat. Okay, r hat means r vector hat, I mean. Okay, so it will be multiplication by position vector r. It will be simply multiplication by position vector r. It will mean like this. Okay, so if x, y and z directions are specified, then you will have to use the we will have to substitute x, y or z there. If position vector r is there, then you will have to substitute r vector over here. Okay, so this such is the thing. Now linear momentum operator, as already described in the previous class. Okay, it is simply px hat or capital Px equal to minus I h cut del by del x. Okay, minus I h cut del by del x. Py hat or capital Py is equal to minus I h cut del by del y. Pz cap or Pz is equal to minus I h cut del by del z, right? And similarly, if we generalize this, okay, if we generalize this, then it will be equivalent to this. These are for x, y and z directions. Okay, but if we generalize it, so it will be equal to p vector hat or capital P vector. Okay, so it is denoted like that. Okay, the operator is capital P operator vector. Okay, it is denoted like this, capital P vector. So it will be equal to minus I h cut del. Okay, now what does this del mean? Okay, and how has it come? So clearly you can see one thing over here, that your p will be equal to px I cap plus py j cap plus pz k cap. You have learned this. Now when I take the hat, suppose I take it, I convert it into operator. Okay, if I convert it into operator, then what will happen? Instead of this p to corresponding to every observable, there is an operator, right? So corresponding to this p observable, there will be p hat operator. So p hat will come over here. Corresponding to this px observable, this operator will come. Okay, corresponding to this py, this operator will come, and corresponding to this pz, this operator will come, right? So this is the thing. Okay, now when I substitute the values from there, for example, px value is minus I h cut del by del x, py value is minus I h cut del by del y, pz value is minus I h cut del by del z, right? If I substitute those values over here in the expression for momentum, okay, in the expression for momentum, when I substitute these values, over here, okay, then what will happen? Clearly your expression will become something like this, as you can see over here. Okay, as you can see over here, your expression will become something like this. In the place of px hat, you will put this. Okay, in the place of px hat, in the place of py hat, you will put this, right? In the place of pz hat, you will put this, right? So you have put all these things over here, right? So after you put all those things over there, minus I h cut, it will be common factor. Okay, it will come out of the bracket, and after it comes out of the it comes out as common. Okay, I am not talking about that bracket notation. I just simply mean this bracket. Okay, I simply meant this bracket. Okay, so after it comes out of comes out as a common factor, so we are left with minus I h cut. Now this quantity is called as del. Okay, this quantity which has been written over here, it is called as del. Okay, you can either denote it like this, or you can also put a vector sign over that. Okay, both mean the same thing. You can either put a vector sign over it, or you, even if you don't put a vector sign over it, it is also okay. Okay, both the notations are good. So I have not put any vector sign over here over that. Okay, so minus I h cut. So how will your momentum operator look like in 3 dimension? So in 3 dimension, your momentum operator will look like minus I h cut del. Okay, now when momentum operator is applied on psi, you get like this, something like this. Okay, you will substitute this value over here, right, over here. So after you substitute that value over there, it will, this operator minus I h cut del, it will run on this psi and will produce an output, and that output will be p vector, that is your momentum vector. So from operator you have switched over to observable, and clearly it is of the form, operator psi equal to observable multiplied by psi, right? It is of that form. So similarly this is also of that form only. You can clearly see this thing, you can clearly observe this thing. Okay, so let's move on to the next slide. Okay, now potential energy operator, what does this imply? It is also very similar to position operator. Potential energy operator is also very similar to position operator. It is simply multiplication by potential energy. Okay, so when multiplication by VR means potential energy function. Okay, when we multiply by potential energy function, it is equivalent to your potential energy operator. So I have applied this operator on psi, and I have got finally potential energy multiplied by, because it is equivalent to multiplication. So unlike your, it is very similar to your position operator, which was equivalent to algebraic multiplication. Okay, but your momentum operator was different. It was equal to minus I h cut del. Okay, your momentum operator was different. Your momentum operator was not equivalent to algebraic multiplication. Okay, but your potential energy operator and your position operator, those are equivalent to algebraic multiplication. Okay, so similarly your potential energy operator is equivalent to your algebraic multiplication. Means operator in itself is your observable. Okay, you can say it like that. Okay, you can say it like that. Now kinetic energy operator, we will have to derive its expression. So we know this very well, that for non-relativistic motion, the kinetic energy is given by T equal to P square over 2m, right? T equal to P square over 2m, like this the kinetic energy is given, right? For a non-relativistic motion. And as we are studying the Schrödinger quantum mechanics, so it is non-relativistic motion only. We have assumed that it is non-relativistic motion, as well as the spin is not taken into account. So clearly this formula for kinetic energy will hold good. Which formula? P square over 2m. The formula T equal to P square over 2m will hold good for kinetic energy, right? Now when T hat will be there, when it will be taken as T hat, okay, so it will become like this, and when P is there, it will be taken as P hat, right? So this expression corresponding to every observable, as there is an operator. So corresponding to kinetic energy, I have put the corresponding operator. Corresponding to momentum, which is also an observable, so I have put another operator. So in the place of kinetic energy, I have put T hat operator, because observable is kinetic energy, so operator will be T hat. And corresponding to P, momentum observable, I have put another operator which is momentum operator, right? So the operators will satisfy this relation as well as observables satisfy that relation. So operators will also satisfy the same relation, that is p square over 2m. So then after that you can apply the dot product rule. Okay, when I say that p square, you can p hat square. When I say like this, that momentum operator squared, so I can write it multiplication 2 times. Okay, multiplied 2 times. And when I write it multiplied 2 times, so I can put the value of momentum operator over here. So value of momentum operator is minus I h cut del, right? And again minus I h cut del, right? So both of them will be multiplied, and when both of them are multiplied, you simply get minus I. What will you get over here? You will simply get plus I square, okay, h cut square del square, right? You will get like this, divided by 2m, right? Now when I square when the square of iota is taken, it becomes minus 1. So this I square will be replaced by minus 1, and when that will be replaced by minus 1, you will get some expression like this, the expression which is given over here. You will get such an expression. Okay, so your kinetic energy operator looks something like this. Your kinetic energy operator looks like minus h cut square by 2m del square. Okay, your kinetic energy operator looks like this. And regarding the duration of the class, friends, you know this very well that it is very difficult to increase the duration of the class because I don't have enough time, but still I will try my best. Okay, and in one dimension, what will this become? This thing, okay, this thing, the thing which is like this, so it is equivalent to what? I had already told you this, right? It is your like this, right? Plus del y by del x square plus del z by del z, del 2 by del z square, okay, plus del 2 by del x square, del y square, plus del 2 by del z square. So it is basically your Laplacian. Okay, now this Laplacian, when it is taken, okay, so what happens? So when it is taken in one dimension, so your instead of del square which used to be here, this expression will simply when it turns to one dimension, so simply these two terms will vanish. Which two terms will vanish? This term will vanish and this term will also vanish. Okay, so these two terms have vanished from here, so it will be simply equal to del square equal to del 2 by del x square in case of one dimension. In case of one dimension, such is the case. Okay, so similarly now the Hamiltonian operator we have. Okay, so what happens in Hamiltonian operator? Let us see. So in case of Hamiltonian operator, you have something called as conservative system. Okay, and conservative system, what does a conservative system mean? Conservative system means that the total mechanical energy for the system remains constant. Means H is the total mechanical energy of the system. It is independent of time. This Hamiltonian operator will work. Okay, this Hamiltonian operator will work when it is independent of time, when your mechanical energy remains independent of time. So your Hamiltonian operator is equal to sum of your kinetic energy plus your potential energy, right? So which is equal to total mechanical energy, and your total mechanical energy is constant for a conservative system. Okay, so your total mechanical energy remains constant, so it will be independent of time. Okay, independent of t. Independent of t, it means t expression will not come in its t term will not come in its expression. So h hat equal to t hat plus v hat, right? Over here we have got this. Okay, after this you can clearly write this thing, right? H hat equal to t hat plus v hat, right? And h hat will be equal to your, what will be your h hat? H hat will be equal to, after you put the kinetic energy operator, you put it like this. After you put the potential energy operator, you put it like this, which have already been found some moments ago. So you get the Hamiltonian operator, which looks something like this, right? So Hamiltonian operator, it is, when it is called as Hamiltonian operator, it is quite understood that it will be independent of time. When it is called that it is Hamiltonian operator, it is quite understood that it will be independent of time, and the sum of potential and kinetic energy will be a constant. Okay, means the system is conservative. Okay, such is the meaning of Hamiltonian operator. But total energy operator is a little bit different. Total energy operator, now when we say Hamiltonian operator, it is by default that it is time independent. Okay, when we say only Hamiltonian, it is by default that it is time independent. Okay, time independent, it is by default. Okay, when we say Hamiltonian. But when we specify specifically, when we specify that it is time dependent Hamiltonian, when we specify like this, then it will be total energy operator. Only Hamiltonian, then it is time independent for sure. But when it is specified that time dependent Hamiltonian, that will mean that it is total energy operator, and the system is not conservative over here. Okay, the system over here is not conservative. Okay, not conservative. So total energy operator, E hat or H hat, time dependent Hamiltonian, and E hat or H hat will you be equal to your I H cut del by del T, right? It will be equal to I H cut del by del T, total energy operator, right? So after putting all those values now, okay, after putting, not putting, it will be simply equal to this only. Okay, so there is I have not put any proof of this over here. Okay, no need of any proof, just mug it up. Okay, I H cut del by del T is your total energy operator, just mug it up, don't go into its proof. Okay, now angular momentum operator in Cartesian coordinates. Okay, you can clearly see this, that this is the path along which your particle is moving, then some xyz coordinates it will have. Okay, so classical definition of angular momentum looks something like this. Classical definition of angular momentum looks something like this, as shown in the figure, right? Now in Cartesian coordinates, what happens is that center of mass angular momentum, okay, in center of mass reference frame, okay, in center of mass reference frame, angular momentum is equal to your L equal to R cross P, right? Angular momentum L vector is equal to R cross P vector, R vector cross P vector, right? So such is your angular momentum. Now in operator notation, what happens is that we will simply write hat all over these. Okay, hat and hat, that will simply imply that they have become operator. Then after that, for p hat we have already found out the value like this, so we will substitute that value over here, and after we substitute, we will also substitute for r. Now for r hat, what happens is that you will have something like this for r hat, that your r hat will look like x hat cap, y hat cap, z hat cap. Okay, now I had already told you that they simply mean multiplication by x, so x hat I cap, with that will mean x I cap. Okay, so as the position vector is position observable is equivalent to its operator in itself. Okay, it is equivalent to its operator itself. So clearly your r hat is equal to x I hat plus y z hat plus z k hat. Okay, because you will put you will write the value of position vector like this, then you will put hat in order to denote the operator form, and after you put the hat, these things will in turn become, because the operator is observable in x y z direction with respect to position, the operator and observable in xyz direction with respect to position are the same as the observable itself, observable position itself. So operator and observable both are same in case of position, and similar was the case with potential energy also. I had told you similar was the case with potential energy also. Potential energy operator simply meant that it is potential energy, right? So similarly, x hat will simply imply that it is x, y hat will simply imply that it is y, z hat will simply imply that it is z. So when I put all these values in equation number 1, the equation might not be properly visible to you, but because I am making the video with tablet, so in this equation 1 value, put all those values, okay? You put all those values in equation 1, so you get something of this kind, okay? And del also you will substitute, okay? You will substitute del also, okay? So del value you know already, okay? Del value you know already. It is given on the next screen. It is given on the next screen. Now in the next screen you can clearly see that del equal to I hat del by del x plus j hat del by del y plus k hat del by del z. Then L hat operator, what will this imply? You can clearly see this thing, that when I put this value over here, okay, and I basically take the cross product, okay, so these terms, as they are constant, they will come out and it will become something like this, R hat cross del, okay. So it will become something like this. Now after it becomes the cross product of those two, so the cross product of those two can be represented in the form of this determinant, okay. It can be represented in the form of this determinant, and after I denote it in the form of this determinant, I will just arrange the values, okay, because what I have is, I have simply x I cap plus y j cap plus z k cap, okay, in multiplied by, in cross product I have all these terms, okay. So I have in cross product I hat del by del x plus j hat del by del y, okay, plus k hat del by del z. I have all these things in the cross product. So after I take the cross product definition, the determinant will look something like this, and after the determinant looks something like this, I put the values, because x I cap plus y j cap, they are first, okay, they are first, and these are in the second in the order of multiplication. So in cross product the order matters. So as r hat is first in the cross product, so r hat terms will come over here, and as del is afterwards in the order of multiplication, okay, sorry, okay, so as your this is in the order secondary in the order of multiplication. Sorry for some disturbance was there in the between, okay. So after you take that, so what will happen is you will get something like this. Now how will it open? I hat will open like this, y multiplied by this minus this multiplied by this, right? Then j hat will open with minus sign, then you have this multiplied by this minus this multiplied by this, okay, and minus j hat will open like that, okay. Then k hat will come, okay, then k hat will come, and it will also open with this minus this, right? So I don't think there is any need to explain the determinant, okay, it is quite obvious. And after I take those products, I simply get Lx k hat equal to this much, Ly hat equal to this much, Lz hat equal to this much, okay. So this is how the angular momentum operator looks like when it is operated in x direction. When the operator of angular momentum is operated in x direction, we get something like this, and when it is operated in y direction, we get something like this, okay. And it is when it is operated in z direction, it is something like this, right? So yeah, I think you should have made the notes also along with me, but in the form of writing, it is more convenient to make the notes in the form of this PDF. Many students say that it is not very convenient to make the notes because it becomes too speedy, right? Yes, it is right, it becomes speedy, but no need to be worried about it. Okay, so I don't think there is any need to explain this, that this is what is I minus I h cut multiplied by this is what is your pz hat. Okay, minus I h cut multiplied by this is what is your py hat, right? You have learned the momentum operator already, linear momentum operator already. So when you put the values, you will understand this. Okay, so revise the thing today itself, and see you in the next class. The next class will also come today itself.